All right, now before you begin logarithms, it'll be important to start with a graph of an exponential function like y equals 2 to the x. I want to do the graph of y equals 2 to the x. Now when you're doing a graph of y equals 2 to the x, let's get some values. Let's let x equal, pick a number. Let's let x equal 0. If x is 0, what would y be?
2. 1.
2 to the 0 power would be 1, right? All right. What if x is 1? If x is 1, then y would be 2 to the first power, which is 2. If x is 2, y would be 4. If x is 3, 2 to the third power would be what? 8. Let's try a negative number. Negative 1. 2 to the negative 1 power would be 1/2. 2 to the negative 2 would be 1/4. And negative 3, 2 to the negative 3 power, that is 2 to the negative 3 power means what? 1/8. 1/8. Okay? I'm almost out of board. Okay? Now, let's graph the points and see what we got. If x is 0, y would be what? 1. So over 0 and up 1. If x is 1, y is 2. Over 1 and up 2. If x is 2, y is going to be up 4 units. 1, 2, 3, 4. If x is 3, y is up 8 units. If x is 3, y is up 8 units. Okay? If x is negative 1, then y is up 1/2. Okay? If x is negative 2, y is up 1/4. If x is negative 3, y is up 1/8. What do you notice about the points? If you move 1 unit to the right, what happens to the value of y? It doubles. Every unit you move to the right, the value of y doubles. Every unit you move to the left, it's cut in half. Okay, it's cut in half. So if you graph this with a nice smooth curve, this is what we call an exponential function. Exponential function. That is where y equals 2 raised to a variable power. The variable is in the exponent. That's what makes this an exponential function. Well, let's look at another kind of an exponential function. Let me change colors. What if we switched the x and the y around? What if we switched it around and made it x equals 2 to the y power? Now, I'd like to make another table of values and graph these points. Since it says x equals 2 to the y power, it'll be easier to pick the y value first, won't it? Instead of picking the x value, let's pick the y value. Pick the y value. Let's let y equal 0. 2 to the 0 power would be 1, so that means that x equals 1. All right. What about if y is 1? Then 2 to the 1 power, x would be 2. How about if y is 2? Let's let y equal 2. Then 2 to the second means that x would be 4. 3 would give you 2 to the third, which is 8. Negative 1. 2 to the negative 1 would give you 1/2. 2 to the negative 2 would give you 1/4. 2 to the negative 3 would give you 1/8, and so forth like that. In other words, it's the same values we had in the original graph. We just interchange the x and the y, right? So we just interchange the values in the table. Now graph these points. If x is 1, y is 0. If x is 1, y is 0. If x is 2, y is 1. Over 2 and up 1. If x is 4, now we have to move over x equals 4 units and up 2 units. Over 8 goes up 3. Now how about x equals 1/2? X equals 1/2 would be over half, and we drop down 1 over 1/4, and go down 2 over 1/8 and go down 3. You see what's happening here? We're going down along the y-axis. We'll never touch the y-axis, and if you connect these points with a nice smooth curve, you'll see the graph going like that. All right? Now, I want to point out a concept that we had before, and that is the concept of an inverse function. What was it we did when we found an inverse function? We interchanged what? The x and the y? And then we had to solve for y? Well, so far we've done half of that, haven't we? We've interchanged the x and the y. Now notice what the graph does. What if I draw the line y equals x? This would be the line y equals x. Do you notice the symmetry that you have? You notice the symmetry of this graph? The y equals 2 to the x compared to the x equals 2 to the y. The symmetry around the line y equals x. Think of the y equals x as the mirror, and then each graph is the image of the other graph. Right? And that's what happens with inverse functions, isn't it? That's exactly what happens with inverse functions. Now, the next thing we did with inverse functions, however, after you get the variables interchanged, we would have to solve for y in order to see what this other function would be. Solve for y. All right? This was y equals 2 to the x, and this one is x equals 2 to the y, but the big question is, how do you solve for y when y is the exponent? How can you solve for y? You can't, can you? You can't. There's nothing we've had so far that would allow you to solve for y. So what we do in mathematics, when we don't know how to do something, we make up a definition. And this is what John Napier did back 400 years ago. He said, let's take this x equals 2 to the y, and let's make a definition like this. Y equals log base 2 of x. Now that looks like a foreign language, doesn't it? You've probably never seen anything like that before. If this is the first time you've ever seen logarithms, I know it's the first time you've ever seen that. But what this means, the way this logarithm is defined to be 2 to the y equals x. So this is what we call logarithmic form. Logarithmic form. And this is what we call exponential form.